All right, good morning, everyone. I've been asked by quite a few people over the last year, so either as a question or as a comment, CRIN should really do a project status update for those projects that won the funding competition. And I'm excited to say here we are. This session will focus on the novel hydrocarbon extraction projects under the Reducing Environmental Footprint competition. This is the fifth of these such sessions, with the next coming up on June 22nd for projects under the Low Emissions Fuels and Products competition. For those that I haven't met, my name is Stephen Arseniuk. My day job, I'm with Pathways Alliance as the Director of Net Zero Technology. I like to say that my volunteer gig is here at CRIN, though, my real passion. I'm the theme lead for the novel hydrocarbon extraction theme here under CRIN. So that's one of the 7 themes that CRIN has. I'd also like to say novel hydrocarbon extraction is a way of reimagining how we produce oil and gas and other hydrocarbons in Canada, whether that's from Atlantic offshore through Saskatchewan and Alberta, all the way to Northeast BC. And so through collaboration, we can improve efficiency, profitability, and sustainability. Within our theme, we're made up of a number of producers, academia, applied researchers, government representatives, and government funders. Our theme has run a number of panel discussions and workshops over the years to help accelerate innovation in our sector. And if you're interested in talking more about what you're trying to do as part of our ecosystem, please do reach out so we can find a way to get you the help to accomplish what you're trying to accomplish in our system. Just make sure that I'm getting the right button here. There we go. For our land acknowledgement today, it's an important step towards reconciliation. And in the spirit of reconciliation, we acknowledge that we live, work, and play on the traditional territories of the Blackfoot Confederacy, including the Siksika, the Kainai, the Piikani, and the Treaty 7 tribes comprised of the Tsuut'ina, Stoney Nakoda Nations, and the Métis Nation of Alberta, Region 3, and all the people who make their homes in Southern Alberta. I'd also like to acknowledge some of the STEM professionals that are joining us today. Cheryl and Pat provide STEM newcomers to Calgary with information on Alberta's energy ecosystem and its talent requirements through a CCIS project funded by the Government of Alberta. Today's event falls on the final of 8 mornings of their programming. So for those that are joining us today from that program, I'd invite you to stand up and just wave and share who you are so that we can see you today. Yeah, congratulations. Yeah, welcome. These people are attending in person along with the cohort of educated and experienced energy professionals that we have. It's vital that our industry attract new talent and support their networking, and we're extremely pleased to have you join today. So thank you very much. So a little bit of housekeeping. We are using the Zoom webinar as our platform today. For in-person, our audience, please do not join the webinar, as this will create feedback and issues in this space. To pose a question for members in our in-person audience at the Energy Transition Center, please do raise your hand. Amber and Sally will bring you the microphone. You can say your name and affiliation. For those that are joining us online as part of our virtual audience, please use the Q&A feature on the bottom of your screen. Include your name and affiliation. If we require you to elaborate further, the staff will say your name and and unmute your microphone for you to ask your question. And so for our agenda today, we're joined by 3 presenters, 1 in person and 2 virtually. I've been interested in all 3 of these projects since they were first announced for funding through the Reducing Environmental Footprint competition, and I'm excited to learn about how those projects are progressing. We'll have each presenter present and then take questions collectively at the end. So each presenter 1 at a time and then a group set of questions. For those that have joined us in person, we do encourage you to stay for the coffee and the networking afterwards. All right. And so for our first presenter today, we're joined by Haibo Huang, who is the Director of Energy Services Division at InnoTech and the manager of ACCI Research Program. It's a large consortia research program with industry participants and the Alberta government. He has been with InnoTech Alberta, formerly Alberta Research Council and Alberta Innovates Technology Futures, since 1997. The areas of his research include in situ bitumen recovery, process development, mechanisms in solvent-based and chemical-assisted EOR processes, multi-phase flow and porous media, and petroleum fluid characterization. So please join me in welcoming Haibo virtually.
Thank you, Stephen, for the introduction. So could I share my screen now?
Yes, please.
Okay. Can you see my screen?
Yes.
Good morning, everyone. And I'm really pleased to be able to, join this opportunity to give an update on the project InnoTech got awarded under the CRIN's funding system. So this project is a CRIN 2022-014 project. And it is the accelerate advancement of a DME-assisted bitumen in situ recovery process. So the project, well, I have some difficulties in moving. I don't know why I cannot. Okay, so it takes a little bit of jiggering. So everybody knows currently the in situ bitumen recovery process using SAGD faces a challenge with a high GHG emission and pretty high water usages. And in order to achieve the 2050 net zero target, new recovery process with lower GHG emission is essential. And this DME-based in situ recovery process is really, scheme speaking, uses the SAGD well configuration by injecting wet dimethyl ether. It's kind of solvent, novel solvent, into the bitumen reservoir at moderate temperature. And the previous study, up to the point when we applied for this CRIN project, had basically advanced through 2D lab scale model experiment that demonstrated this process scheme really shows very significant reduction in the energy consumption, means less GHG emission, and use very little water, saving a lot of water. Subsequently, we ran the 3D large physical model experiment that demonstrated the performance of this process scheme, which will be able to produce bitumen very much comparable to the SAGD bitumen production rate. So you can simply say, okay, it produces bitumen similar to SAGD with 80+% of reduction in GHG and water usage. So the process development had reached to the TRL 6, and this CRIN project really is intended to take this process development further to approach or achieve TRL 7. So that's the objective of this CRIN project. And the progress of the project to date is summarized here. I use the table format. This project has 6 milestone deliverables. Milestone 1 is really develop a field scale DME process predictive tool, which is a simulation approach. And it has 2 parts. One is detail the numerical history match of the 3D large experiment and incorporate all the key mechanisms into the prediction tool and use that tool to forecast the process performance at field scale. And this milestone has been completed now. The second milestone is to evaluate the potential startup method to this DME process using simulation and lab testing approach. The simulation to assess the potential schemes to start this process had been concluded, and 1 and 2, promising schemes that come out from this simulation will move into the lab testing stage. So we can say the M21 is completed, M22 is underway. So the third milestone deliverable is the design and estimated cost of the surface facility to support operation of this DME in situ bitumen recovery process. It has two parts. One is to develop the flowchart for two models. One is to support a pilot test of this DME process. And the second one will be the process, the facilities required for a commercial project at 40,000 barrel a day production capacity. To date, the flowchart development for the piloting model has been completed. We were moving into the cost assessment part. And the development of the flowchart for the commercial operation at 40,000 barrel a day capacity just got initiated. So this milestone progresses well. So milestone 4 is experimental 1. Will be a 3D physical model experiment on the SAGD. You may ask why is SAGD? And this is a retro study because any solvent process will need to know whether or not it can further reduce the residual oil saturation in relationship to the overall recovery factor. And it has two parts. One, set up a large 3D physical model experiment. Now the model setup has been almost completed. We anticipate the experimental run will start in July, next month. And after that one, there will be the so-called post-run analysis to get all the experiment data completed. So that milestone progressed well. Milestone 5 is the optimization of the DME bitumen recovery process, which will shortly start, following the halfway through of the milestone 4. And the milestone number 6 is one for the IP protection strategy, because this project indeed will have the potential new IP being developed. We needed to know how to really advance and protect the new IPs. And importantly, the environmental impact assessment of this DME process at the commercial scale need to be, conducted, and knowing the key part, as it progresses. And the last piece is compile all the data and finish off the project report. So here is the where we stand per project progressing. And I want to make clear here is why this project is supported by the technical resources from the 3 major oil sands operators, Suncor, Imperial Oil, and CNL. And the simulation modeling support comes from CMG, Computer Modeling Corporation company, and the surface facility design will be supported by a specialized engineer company. Is the Scotland engineer. So now, what are the good part and some challenges the project has been, experienced during the course of the project execution to date? The good part is this one. The key technical resources for the project execution, they're all available at InnoTech. And we had a strong technical support from the partners, CMG, CNL, Suncor, and Imperial Oil. We have confirmed the required external resource to support the project, which is a surface facility and design and cost estimate. That is a scope one which has been confirmed. So project task generally follows the schedule. And yeah, like any experimental project, it will have some operational challenges. One obvious one is the scheduling the technologist for the task with the lab experimental part, which is milestone 2.2 and milestone 4.1 is the tighten and following up, make sure the committed resource always available on time. But it is manageable. We have to put a lot of effort to ensure things going the way it should. And then one piece we are working on that one is to confirm the external resource for the task M32, which is environmental impact assessment of the DME in situ process. InnoTech has internal capability doing the environmental related assessment, but we would like to use very much specialized organization to do the work, definitely to meet the project deliverable requirement. So what is the next step? This project will continue the execution of all the project tasks and the milestone deliverables. So project stay on course to progress. And just one thing I want to share with everybody here, it's under the collaboration opportunities, which the project seems to be beneficial to the recipient to expand the scope, is to update the development status of one technology that is the one to make DME from methane in one step. That technology is currently being developed and close to the pre-commercial. The reason why I want to raise this one is this: during the project execution, industry companies asked, it would be good if the DME can be made on site where it's being used for in situ recovery. Well, in order to do that one, this technology to make DME from natural gas in one step in a fashion near the operational site would be a positive add to if the process go on commercially deployed. So that is one thing I just want to share, in expanding the scope to cover that one, will add the value to the project. And so that is the update. And thank you very much for your time. So I can give back the screen to the chairman. Thank you.
I hope everybody enjoyed that as much as I did. Yeah, really appreciate your time and update today. Up next, we're joined by Katrina Stewart from Cvictus. Katrina is a process engineer with Cvictus, working on both the energy project development and as part of the biotech division. Ms. Stewart previously worked as an environmental engineer with experience in regulatory, air dispersion, and hydrogeology assessment, field supervision, and fermentation operations. She is also an entrepreneur with experience starting up and operating a distillery in Scotland. Ms. Stewart holds a Bachelor of Science in Chemical Engineering from Queen's University in Kingston, Ontario, and a Master's of Science in Brewing and Distilling from Heriot-Watt University in Edinburgh, Scotland. Please join me in welcoming Katrina. Thank you.
Hi, everyone. Great to be here. I know some of you were expecting Rob Sturgis, but he had a conflict this morning. So you're stuck with me, sorry. As mentioned, I'm an engineer with Cvictus, and we're here to talk about our first project, the Mannville Enhanced Hydrogen Recovery Project. So our main objective is to develop this first commercial facility using our patented enhanced hydrogen recovery technology. EHR was designed to produce low cost, low carbon hydrogen at a large scale to assist with the energy transition and materially reduce GHG emissions. We're building the first of its kind facility here in Alberta, and we're on track for production in 2024. As you may realize as well, one of the big challenges with the hydrogen economy is that we're stuck in this chicken and egg scenario. So a market or a new market doesn't quite exist. So new production methods aren't brought online and the infrastructure isn't really built, but that means a new market can't really get established, right? So kind of a what comes first scenario we're stuck in. How we've tried to fit in there is that by producing 7 tons a day of clean hydrogen as our first product, we kind of come in at a sweet spot where we're commercially viable, but we're not actually stretching the limits of the market or the systems in place at the moment. On the technology front, we have created a new way to use conventionally dirty hydrocarbon resource in a clean manner. Helping reduce GHG emissions, fresh water demand, and land use compared to the incumbent methods of hydrogen production. So this is a huge project for us. It is the main priority of our company. This is where all of our efforts are going towards right now. And we've made significant progress with the help of CRIN. We've completed a major resource recovery program here in Alberta last year at our site. So we extracted a huge amount of core for analysis. We completed testing at the site. We have equipment and monitoring devices downhole still. And we also completed a large CO2 injection test to gather better porosity data and understanding of our reservoir behavior to confirm and better or update our models. We also submitted 2 of our application approvals to the Alberta Energy Regulator. So there's one for the underground in situ scheme component and one for the surface hydrogen facility. Both of those are expected relatively soon. On the engineering front, the plant is all ready to go, and the design of the wells is coming together relatively well. We also have a detailed plan for the hummocky terrain where our site is to make sure that we maintain natural drainage in the area, but also save space for expansion in the future. There we go. So there's always challenges and lessons for a facility in a project of this size. And then you throw in a pandemic and supply chain issues and new technologies. And I'm sure you can all imagine some of the general challenges that we faced, and maybe you've experienced them yourself recently. But here are a few that are specific to ours. So for our large CO2 demonstration, we actually had a really hard time to source and supply the CO2, especially when as a society, as an industry, we seem to have an excess of it, right? So we're right by the carbon trunk line, but even if you could get it out of the line, most of the trucks on the road are food grade CO2 trucks, and they won't accept industrial CO2. There's also the fact that that CO2 in the trunk line is associated with carbon credits. And so we would have to be liable for that. And as a demonstration, that's not really feasible. We ended up considering a few other options, but we needed to end up purchasing food grade CO2 to just pump down a well, which was extremely expensive and not something we were anticipating. Our regulatory pathway here in Alberta is relatively clear. It's one of the reasons we chose to be here in Alberta. And in our schedule, we put 9 to 12 months, and it's 12 months. So it's, while it might not seem like a challenge, it is challenging to just kind of sit there and wait for your approvals to come in. On our design and engineering, we are absolutely razor focused on making sure we maintain low cost as well as low carbon. But everything has an impact to every part of your design, right? So if you make one change in the efforts to reduce your carbon, it might end up impacting your utilities, your cost, your power demand, right? So we really have to look at your design from a holistic point of view. And specifically on our gas cleanup and our power generation, it required quite a few iterations to make sure we found that correct balance. We have a really good working relationship with the University of Calgary. They have been really helpful with our CO2 injection test and then our behavior modeling. The team is actually working together to present at a special session this month down in Denver at the Unconventional Resource Conference. And the next steps really are just to finalize everything. We need to start moving dirt. We need to start drilling wells. We need to cut some big checks and buy some equipment and start building the facility. So just to wrap up, we're really excited and proud of the progress that we've made, especially because our core team is so small. But this technology has a huge potential, and we're really grateful that CRIN has decided to help us out on this first project and think outside the box a little bit. So thank you.
Again, that was fantastic. I really appreciate that update. I know, at least for myself in particular, once I heard the funding announcement initially, that was one that I hadn't heard about in the ecosystem ahead of time, and had reached out and connected with Cvictus right off the bat. And it's great to see that you've been making some good progress here over the last year or so. I guess just a reminder for those that are in the room, we'll come back to the group questions. So write down your questions or keep them front of mind. For those that are online, yeah, please do get them in the Q&A, and we'll make sure we have a really good, robust question and answer period after our third presentation here. So up next, I'd like to virtually invite Jiwon Lee from Suncor to take the podium. Jiwon is a project engineer in non-aqueous extraction for this non-aqueous extraction project. He has a Bachelor of Science in Materials Engineering from McGill and an MBA from the University of Alberta. He has been working at Syncrude for 16 years, mostly in research and development and technical operation support. So please join me in welcoming Jiwon. Welcome.
Thank you, Stephen, for the introduction. And thank you for CRIN for the opportunity to share our project progress so far. Before I start the main presentation, I would like to recognize that the non-aqueous extraction, or NAE in short, is a product of unique collaboration between Syncrude R&D, Imperial Oil, and small medium enterprise participant, Exergy. I call this a collaboration unique because it is a rare example of major oil sands operator developing a competitive technology together. And success in this joint development agreement may pave pathway for further collaboration between major producers for competitive technology development. Next slide. Okay, yeah, I'll follow the standard agenda, just like two previous presenters. So let's start with this one question. When someone mentions oil sand, what is the image that comes to your mind? When you use search engines, most images are about tailings pond and large disturbed land due to mining activities. So what if I tell you that we can change that? That there is a way to avoid making any new tailings pond like the picture on your left. There is also that we can reclaim our site progressively to reach the picture on your right many years ahead. And to some process engineer in the crowd, that lower grade ore can be processed without keeping you awake at night. So does this sound too good to be true? With NAE, all this can become a reality by using solvent instead of hot water. Hence, non-aqueous extraction name came from. Because of solvent, bitumen is resolved with greater efficiency. and oil sand clays, which are mostly hydrophilic, agglomerate into coarser particle, unlike water-based extraction. The combination of these factors allows NAE process to be almost agnostic to oil sand quality while producing dry tailings, therefore leading to a much simpler mining operation while avoiding long-term wet tailings storage. The objective of this project is to make this dream come true by bringing NAE process beyond the bench scale test into a continuous pilot operation that would provide scale-up and economic factor for commercialization. So what have we been up to? This project is one of a rare example of JDA between major oil sand companies, which had decades worth of NAE knowledge and over 50 patents developed independently. Hence, validating and absorbing the knowledge alone was quite a task. But the effort paid off with the development of 21 unique flow sheets and several patentable technologies. And ultimately, with breakthrough flow sheet. As shown on your right, we were able to improve safety while reducing greenhouse gas intensity, cost, by applying the novel technology. So what was the challenge? Although I have already mentioned it just a few seconds ago, let me just repeat it. Finding a safe economic process that will not only eliminate tailings pond, but also reduce GHG emission was a challenge. It took us a good part of last year just to answer this question alone. Furthermore, we had to ensure our novel technology is realizable beyond small-scale bench test, while not forgetting to ensure that our mature technology is applicable in NAE process. So far, we've been successful in this journey by uniting our team under one cause to be the last NAE team to change the future. This unity is especially important because of we are from different companies with independent NAE R&D history. Of course, keeping agile work practice, clear project priority, and communication has also been important for our success. So for collaboration, we are always open to great referral, fabrication such as fabrication vendor, rental equipment outfit, and experienced pilot operators. And of course, being R&D activities, we are also open for testing new instrumentation, control technology, and advanced analytics too. So what's next? We are currently working towards 2025 pilot plant startup. This plant will provide valuable operation and process data that will be crucial in determining the economic and scale-up factor for commercial NAE deployment. This involves not only validating the novel technology and managing its associated risk, but also working on pilot plant engineering activities. And thank you for your attention.
And thanks, Jiwon. That was a fantastic presentation as well. Again, lots of good progress and more to come in the years ahead. So now it's time to shift to our question and answer period. And so perhaps I'll ask Katrina maybe to join me at the podium here. And then we'll invite the presenters online to turn their mics on. And yeah, here in the room, we've got a microphone, so please raise your hand and we will get a microphone to you so the online folks can hear. So I think Amber is coming around on the back there with the microphone. And for those that are online, we'll have, as I indicated, our staff read out your question. And if we need to double click or go deeper, we'll unmute you. So thanks for that.
Hi, Cheryl Knight with Talent Needs for the Evolving Energy Ecosystem. So my question is about talent needs, of course, and obviously for pilot projects, we know it's limited to, the direct owner partner companies, but especially in Katrina's presentation, I saw a whole value chain and partners that provide the opportunity for perhaps less visible employment opportunities, especially, as you move through into commercialization. So maybe you could just expand so that we understand the value chain and how employment might be available and even the type of talent you might need. So this is for Katrina, but anybody else who would like to say anything? Thanks.
Sure. So at the moment, we are going to be a hydrogen producer. So the value chain of the hydrogen is kind of at our plant gate. As it pertains to employment, right now we're a really small team, and we tend to utilize expert consultants and outside groups to fill in the space that we need, just because we are a startup, we are a small company. In the future, we will need to expand to fill the needs of this facility, as well as some of our more global plans. We have big aspirations to do this type of facility all around the world, as well as expand this facility here in Alberta. The type of people we'll need is we need experts on and people willing to learn our technology. So it is a bit of a blend between geology and reservoir engineering and hydrogeology, and mining, right? So it's a new type of discipline. And so we're looking to work with the University of Calgary to actually set up a bit of a curriculum to help develop that skill set for our technology. While we do that, we'll need people both at our site as operators. We'll need people to help develop the project engineers at the surface, engineers for underground. But that's kind of slightly down the line for us. I hope that answers.
What about your partners in this development stage? You mentioned the drilling company, you mentioned civil works, and you mentioned the service plant.
Sure. So Sure. So we don't have a specific drilling contractor that we're working with, but there's lots of great small and large ones here in Alberta with excellent skill sets. On the civil side of stuff, we've been working with environmental consultants all around. So, and environmental consultants. If you're interested, I can chat with you afterwards. I don't want to spill the beans on anything, but, and then we're working with a small company down in Houston actually to do the engineering design work. Yeah.
Hi, thank you very much, all of you, for the presentation. It's been very interesting. Pete LaFontaine, with a CRIN member and with chairman of Rainforest Energy Corp. My first question is to Haibo. You refer to a physical model? Is that still a computer model, or are we talking physical kind of properties? So are you still in a computer modeling phase? First question.
Okay, just to clarify, sorry, I didn't make it that clear when that point was touched. Physical model is the experimental lab scale experiment model. You run, you can say, okay, experiment, which is physically simulate the process.
Still simulated then?
Yes. So here is one. The 2D lab model is relatively smaller in the size. We call it the scaled model, where the condition is not exactly, match the reservoir condition, but the 3D large model, which is at the size or the physics or the forces concerning the in situ process are adequately represented. That is pretty good. We call it the elemental, physical model. The result could be closely, looked at using it for, scale up.
Yeah, I get it. I get it. Thank you. Katrina, what volume of CO2 are you looking for? Do you have a ratio?
Sure. So the I didn't get into how our technology worked just because of how our timeline was. But our technology, we capture all of our CO2 from our production and we inject that back underground. So it is directly related to how much gas we're producing. So we have an in situ gasification underground. All the gas that comes to surface, we take the CO2 out of that and inject it back underground for sequestration and also for part of our enhanced hydrogen production.
But you said you had to purchase it, kind of, so
that was for our demonstration to make sure that we were able to, so we had a demonstration test to verify parts of our patent. So we had 2 injection wells, and that was 1,500 tons of CO2 that we injected over the course of a week.
I think you're brilliant. So good thing you showed up. So thank you. NAE question is that surface or the water that you're talking about, is that just less water use or is that just less surface water visible that is kind of the image of the oil sand? So, thank you.
Literally, we do not need water. Amount of water we only gonna use is to make sure the agglomeration to occur. So you're looking at like 0.1%, 0.5% ish of water content, water we may add, or slightly more depending on the feed quality. We're still narrowing that number down. But the amount of water we add is looking at like 1% or less potentially of total oil sand mass that we're gonna treat. So think about that's all the water at the end gonna come out because our product shouldn't contain much water. So our tailings obviously gonna have just that water.
Thank you for the great update on the projects. I'm Mariam Omidwar with InnoTech Energy. My question is for Haibo. I was wondering with the update you got from the experimental and the simulation, if you have any estimation of the recovery rate for the DME in the process. And also the next question is about that, what do you expect it to be the production size of the DME on site if the SACD user are gonna use DME instead of the steam?
Okay, thank you very much. For the first question, and is this one. For the lab experiment, the solvent recovery is always high because the physical model has the good model boundary where there's no material, can go beyond the model boundary. But then you look into the reservoir and where such a physical model, physical boundary does not exist, is part of the process, how you manage operate the process to ensure the solvent, like the DME used in the process, is pretty much stay within the chamber, not to migrate too far. There will be strategies how to achieve that. And so talking about make the DME available on site when, say, you can use it in replacement for steam. That is why I added to the very end of my presentation is, will be benefit to expand the scope of this project, looking into the new technology that makes DME from natural gas, which we have plenty in Alberta, and one step, which means that you have one plant or one, operation line to convert methane into DME that can be used directly by injecting into the reservoir. And because that technology is now it's called the pre-commercial. And I believe we see, looking into the status of how far from the, commercially being used for that technology. And if it's very close, then the possibility will open up. You have relatively small modular type of plant to make DME on site or near site of the in situ recovery. Just use methane as the feedstock and convert it to DME. Thank you for your question.
Thank you.
Hi, Katrina. My name is Mayowa. I'm with the STEM program at CCIS. So in your presentation, it was stated that you had completed the optic fiber installation. So I want to ask, are you the optic fiber installation, are you measuring for both temperature and pressure or just one or the other? And also, did you use a single mode optic fiber or multi-mode, and what was the factor responsible for the choice of one over the other?
Sure. So I'm a little out of my depth on this question, but I'll do my best to answer. So we installed, I guess, a fiber optic cable into one of our two test wells. And it measures temperature and pressure, and it's not a discrete point. So we can measure the entire length of the well. And that was really important for us during our CO2 injection test. So we injected CO2 into the other well, and we helped, it also, we did seismic with that as well to understand the movement of the CO2 and to understand the distance and the behavior of it. And it'll be a key part of our ongoing monitoring of CO2 when we start injecting it. I can put you in touch with the people who know more about it. Yeah.
Thank you.
Hi, this is George Pringle. Hi, Katrina. Question: 7 tons per day of hydrogen that's getting produced, is it expected to be commercial grade hydrogen, 3 nines, 4 nines? And what's the expected outlet for that? Do you have a buyer?
Yeah. So at the moment, it's going to be commercial grade. It's not going to be fuel cell grade, but we could make it there if we just add on another couple PSAs to get to the higher quality. And that depends on our end user. At the moment, we have pretty solid discussions to take that 7 tons a day and move it into vehicles that are using a diesel retrofit system to be used in Alberta and BC. So that's our primary target for it right now, but we're also in discussions to blend it into pipelines. And there's a different, as you mentioned, quality for that needed, and also a different price and carbon credits associated with where it ends up. So nothing's signed on the dotted line, but that's kind of where we're approaching it.
Hello, Katrina. My name is Joel. So my background is in ESG. So my concerns are with the hydrogen production, because from what I've read, most people struggle with water use. So since you guys are in the production phase, how did you crack the code with regards to water use for the project?
That's a great question. And it's key to why we think our technology is so scalable and so beneficial for this industry is hydrogen. Yeah, it requires a lot of water. Water is a main ingredient to make hydrogen. It's not just a utility. And the way that we use it, it's not electrolyzers using fresh water. The water that we use is actually in the formation 1 kilometer underground. So it's gross saline formation water that makes up the majority of the water that's utilized in our process. And there's no other use for this water. If you brought it to surface, it would just scale up all of your pipes, all of your facilities. It's not a freshwater resource. And so part of our application with CRIN was demonstrating our net benefit of using our process other than other hydrogen production techniques when it comes to freshwater use.
We have a couple of questions online for Haibo. First, what is the DME cost per gallon?
Okay, and so I give you the number which we did the assessment economically. Right now, the commercial price for the DME for the industry used not for the laboratory agent, is about at 60% of the diesel cost.
Another question for you. Is there any evidence from the lab studies from theory that DME losses in the reservoir will be any different than observed by the industry to date in pilots and light and heavy hydrocarbon solvents?
It would be similar because the DME loss, if we're talking about the permanent loss, that is somehow absorbed and never dissolved. And similar to, for example, other hydrocarbon have been, studied or even tested, like propane, butane, hexane, and the mixture of those. And so that is one part. Another part is DME has a pretty decent, solubility in water. That is why it's called so-called neutral solvent. And the recovery process using DME will require careful, reservoir management and the process control, not to have the migration of water, further away from the reservoir portion impacted.
And follow up to that, what are your specific expected recovery factors of the DME?
This is the one from the economic, requirement. The DME recovery, in the process, percentage speaking per, injected, it should be 85% and higher.
Thank you. A question for Cvictus. What are the projected production costs in dollars per kilogram of hydrogen? What is the expected carbon intensity of the hydrogen in kilograms of CO2 per kilograms of H2?
Sure. So this first facility is 7 tons a day, and it's the smallest commercial facility that we can run. So a lot of our projections are for a full-scale facility, which will be 10x effectively of what we're building. And there are a lot of economies of scale and things like that that we hope to imply or gain when we get there. For this facility, for our full-scale facility, our CO2 intensity will be roughly 0.88 tons of CO2 equivalency per ton of hydrogen. And we're aiming to be cost competitive with gray hydrogen right now. So $4 to $6 per kilo at plant gate kind of thing. And this first facility has a higher CO2 emissions just because it's smaller. I think it's more like 3 tons of CO2 per ton of hydrogen.
Thank you. One last question for Haibo. What temperature ranges are needed in the reservoir for the DME to work?
Oh, for this process, it has the range. And the intention is not to have temperature too high. That is why we call it the moderate. Let's say, okay, between 60 to 100 in that range. So it is a variable, not necessarily at 1 or very narrow banded temperature.
Thank you.
Great. I think we have time for another question or two if those questions have begot more questions. So I'll just pause and see if any have come up. We do have one more at the back, so.
My name is Edward Sang. I work in the external innovation team at the Alberta Energy Regulator, but I do have a mining engineering background, so I do have a question for Jiwon for the NAE unit. It's great to hear you guys can reduce the water content in the so-called dry tailings, which is the product of your NAE process. My question is how competent would the material be in terms of geotechnical perspective compared to, say, overburden material or interburden material from the mine? to be constructed as a dump or a dike in pit. I suppose that's how you come up with the 1/3 reduction of the footprint, environmental footprint.
Yes. So part of the 1/3 reduction is also we disturb a lot less land, because right now currently many water-based extraction does require a bit of a blending. So you do have to open up, not by economic or environmental choice, because you just have to make a blend to make the process work. Our process is not expected to require that stringent. I'm not saying there shouldn't be any blending, but a lot more agnostic to the quality. So that is a factor of it. And another factor is also into that 1/3 is that we can do progressive tailings area reclamation without any just dry landform. Literally, you fill it up and plant tree, and you should be just already starting the reclamation while you're operating next door. The solid we are getting out so far, that we have created to simulate, so far suggests that is actually, I think, on par with overburden, and actually obviously lower hydrocarbon than interburden. And the moisture content wise, actually we're a bit drier. So we actually even consider potential re-wetting which means that we may even consume water there is leftover. We may even consume those, but like we don't need to. But after consulting with some geotechnical folks internally, like there is the optimal moisture content. Probably you know better than me on that one, but like we will re-wet it to make it happen. And if you don't need to re-wet it, will be energy saving, because running additional equipment is additional energy intensity. So we have to optimize those. But right now we are actually on drier side of the solid quality coming out of our tailings process.
Did you mean there will be like more blending with other material to make the dry tailings available for, like, say, RTR criteria?
No, there shouldn't be any blending required. As is, it's going to be majority solid. I would say 5-6% moisture content, most of them solid, and trace amount of hydrocarbon. That's what we are expecting from our tailings process.
Okay, thank you. I do have one follow-up question. That's has there been any studies or pre-feasibility studies on how the dry tailings will be transported? Like I assume you guys will be using trucks, but then would there be more emission coming out of the fleet?
We are actually in process of doing that assessment right now. I just kicked up the meeting yesterday on that aspect because we've been emphasizing a lot more on process and tailings soil quality, but we are actually starting that assessment. But right now, the very high level economic assessment assume we use tailings, but the GHG aspect of the moving the tail towards the open pit area where we can just fill it up and start the reclamation, we need to include that in the assessment. You're right.
Great. Well, thank you for those insightful questions and insightful answers as well. I know I learned just as much from those as I did from the presentations themselves. So thank you for those. I know we're at about time here today, so I guess I'll draw this to a close. Would like to again thank our presenters for their presentations today. Would really love to thank those that joined online, and in particular those that have joined in person today. You know, it's fantastic to see people back together and having an opportunity to network. I guess on that note, for those that are here in person, I mean, we still have a little bit of, you know, snacks there, some coffee. It'd be fantastic if you could stick around and either connect with the speakers or each other. And just a final reminder to also, if you're not a current CRIN member, consider joining CRIN. I know I get a ton of value out of my time, not just as a volunteer, but also as a participant. And you don't need to be a volunteer in order to join. I can attest to that. So yeah, it's a free membership. You take a social pledge and agree to help the ecosystem where you can. And such a great organization. So thank you all again, and we'll see you soon.